Okay. This is X-Ray Production. My name is Marcus, and here we go. So this is the circuitry for the X-ray machine. Uh, I'll get to all the details as quickly as I can. First thing I want to say is pretend like we're going to have a patient. Patient's going to want, you're going to want to put the patient at 120 kVp, 25 MA for 3 seconds. Those will get programmed, and I'll show you where. The first thing to note is the incoming line current that comes from the electrical company to your building starts off at 220 volts, 60 hertz, but they don't give that to all the buildings in town. Most of the buildings in town have 110. So because 220 is too hot, they convert it to 110. 110 is what we're going to use for our X-ray machine. That's going to go in wherever it's plugged into the wall, and you're going to turn on your machine at the main switch. All right, first thing that happens when you turn on the machine is electricity rushes to the other side of this whole system, and it warms up the cathode and the anode, and I'll get to that later, why it does that. But at this point, this is when the patient will be put on the table and everything prepped for the X-ray, just to give the machine a chance to heat itself up. So you turn on the machine, it's warming up the other end, but simultaneously, all three of these circuits are getting juice. So I've got a circuit over here, I've got a circuit over here, and I've got a circuit over here. All right, and it's going to complete all this instantaneously because electricity moves super fast. All right, but let's talk about the filament circuit first. So the filament circuit is this run right here. It's going to have an MA selector. It's a variable resistor. That's where we're going to put in that 25 MA. All right, so we program that in the machine. It's on the filament side. Okay, very quickly, I want to go over induction because you'll note right here the circuit is not connected. In this drawing, that's intentional because everywhere the circuit's connected, solid connection is displayed as such. This is induction. Induction happens because all electrical current has an electrical field around it. That electrical field will carry the electrical current across a gap. Not a very large gap, but it'll cross a gap. That allows this system to maintain its independency from the other system so that the machine doesn't get confused. When I put the MA in down here, and you'll see in a moment, I put the kVp up here, those two things aren't getting mixed up and the machine can accurately provide the juice that we're asking for in the various compartments. So our 25 MA is going to be on the side of the filament. We can skip this. And it's going to cross over again through induction in this step-down transformer. This step-down transformer has many coils on our primary side and fewer coils on the secondary side. That's intentional because now the 110 volts that we have on the one side becomes 5 to 15 volts on the other side. And that's all we need to get to that filament to make sure that we don't burn out the filament. This is all we need. Too much juice, filament breakage. That's one of the problems with the tube, the filament could break. So we avoid that by reducing through a step-down transformer on the filament circuit side. On the primary circuit side, we're going to have an auto transformer. An auto transformer is a very special type of transformer. It also uses induction. You'll see another arrow with another gap, right? But you can select where it connects over to this. On this type of transducer, all of these coils pass juice to all of these coils, but not all of the juice gets accepted because there's fewer coils. Over here, we're going to direct to the specific amount of coils that we want. We do that, we put in our 120 into this voltage switch. We tell it that's what we want, and it automatically adjusts itself. Okay, so then this circuit will have the 120 going through it. You'll note right here, there's another switch. It's a timer. That's where we put our time in. Okay. So now, when we're ready to get our juice to cross over for this one, we'll depress that switch. When we do that, this is a step-up transformer. Our 110 in these minimal coils are these tightly packed coils because they're going to become 10,000 volts on the secondary side. First thing that's going to happen is we're going to hit this meter. This meter is going to do two things. It's going to make sure that our MA of 25 times our time of 3 seconds is correct. 75 ms is what it's having passed through it. If that's correct, then the next thing it does is it makes sure that it's 10,000 volts, exactly 10,000 volts. Too much will fry the system. Too little, not enough to produce X-rays anyway. So what it does is, if it's too little, say 7,000, it recognizes that and it won't even turn on. There's not enough force for the out of the electricity to get through that switch to cause a flow through the secondary side. So in essence, there's no flow at all. Conversely, if it's 15,000, a lot more volts, goes to a ground. The switch sends all that juice to the ground and again shuts it off. There's no flow in the secondary side at this point. So we need it to be exactly 10,000 volts, and this meter ensures us of that. Okay. The next thing that happens is that 10,000 volts heads towards some capacitors. Those capacitors are storage units. They can store those 10,000 volts, and they get energized by that. And then the capacitors will send the juice to the falling load generator. Now, the falling load generator is a special element in this thing because what it does is it prevents the 10,000 volts from going through the system continuously, because that's too much. It'll get too hot. Everything will start melting, and that's no good. So this allows 10,000 bursts, which is why the capacitors can hold 10,000, because as this releases 10,000, the capacitors send another 10,000 to the load generator and get recharged. So these capacitors will almost always have 10,000 in them to send to this falling load generator, and it just drops 10,000, 10,000, 10,000. And that gets headed towards these rectifiers. The rectifiers are actually a series of diodes. A diode is a special type of electronic piece. It only allows flow in one direction. The reason it looks like this, you see this line and this arrow, you have a plate on one side, similar to an anode, and a pin, similar to a cathode, on the other side. Same number of electrons in the entirety of the circuitry. But because this is a plate, the electrons spread out on this side, and this is more like a pin, they gather on the tip of this, so they're only going to go from this tip to this plate. They try and come the other way, all these electrons here are opposing it, and it can't get past this point. So what happens is, you have flow coming one way, right? It comes down, passes through this rectifier, goes to our tube, comes back around to complete the circuit. When it's alternating current, switches the other direction, then it comes down this way, the other direction. And that's alternating back and forth. The electricity passes through these rectifiers 4 times. Okay? What that does is it ensures that we get a pulsating DC current heading to that anode. No matter what's going on with this, alternating back and forth, this converts it to pulsating DC to get to that anode. And that's important because we want that anode to be able to spin correctly. We'll get to that in a minute. All this is happening at the same time. Once you hit that switch, boom, all this is going on. So what happens in the X-ray tube? Well, in the X-ray tube, let's go with the filament first. The filament circuit comes in, as we said before, okay? And it heats up the filament. That filament, made out of tungsten, will create an electron cloud around that area, okay? That's called a thermoionic cloud. It's just full of electrons created by, or not created, but released from the tungsten filament when it gets superheated. That cloud, the thermionic cloud, gets projected towards the anode when we energize enough electricity through the system, and there's going to be several things that are happening here. So the cloud starts heading towards the anode, and it's got right here our focusing cup. The focusing cup has more electrons in it than are in that thermionic cloud, which basically forces the electrons in that cloud to head one direction. When they start going all other directions, they oppose the negative force from the cup and have no choice but to head away from the filament. We want that. We want most of those electrons to do just that and head away, but not all of them do. Some of them still do what they're going to do, and they go off in various directions. That's actually the majority of these electrons. Not to mention, the majority of the electricity that we're using is wasted in heat. We need heat to create get the filament hot enough to release those electrons. And once it sends it, only about 1% of all of this effort is electrons heading towards the plate. all of these are scattered from that 1%. So what you end up having is you'll have some of these electrons that came off that tungsten bouncing around, and they'll collect on the envelope. The envelope is this glass outer shell. It's made of plexiglass, and it includes inside of it all of the parts of this except for these stator magnets, electromagnets. So I have the rotor, the anode, I have the cathode assembly, are all inside with the vacuum. Okay, but what happens to these extra electrons is they start collecting on the envelope. All right, and then that causes arcing. Arcing can also break the tube. So two things: filament breakage, tube's done. Arcing on the envelope, tube's done. Okay. But the electrons that do make it to our anode, they're going to make it. Real quickly, some of those electrons don't make it to the envelope either; they just float around, and that causes more problems with the beam because it can interrupt the beam, send electrons back towards the filament itself, and again, less efficient. I meant to say that. Sorry. So the electrons that do make it to the plate, they're going to hit the anode, and that anode is going to be superheated because there's a lot of heat already. Now these electrons moving super fast, they're going to heat that. And if this just sits there, it's going to melt a hole. It's going to pit in that spot. So what do we do to compensate for that problem? Well, we spin the anode. The anode is a disc. It's not this flat thing you're looking at. It's actually a disc. And on that disc, there's a 12-degree angle on the ends where the X-rays are hitting it. As it turns, that point at which it hit rotates away. And then the next point on that disc is what's getting hit with the electrons. And it's moving very quickly. So even though this might only be 3 seconds of hitting it, this bad boy is rotating at a rate of 3,600 to 10,000 rotations per minute. So that spot is going to be hit, and then it's not going to get hit again before all the rest of that disc. That allows every time that spot gets hit to cool before it gets back. So then it doesn't melt in its entirety all at once, the anode. So we spin it. How do we spin it? Well, these stator electromagnets get juiced up, and they cause an electromagnetic induction inside. This is a motor. So what happens is, as you have negative and positive one end, this has a negative and positive on the rotor part, the copper part of the rotor, that opposes, and it's constantly moving to try and move from the opposition to the attraction. So it spins. These will change their direction. There's not just two, there's like 6 of them as it's wrapped around a tube. They'll change their charge, basically, and force the rotor to spin at 3,600 to 10,000 rotations per minute. So that's how that spins over here. You have the various components just real quickly. The armature is this entirety of the thing. It's got the rotor part that's made out of copper, and then it's got a molybdenum backing and rod part to it. And then the anode itself, connected to that while it's spinning, is made out of tungsten with a molybdenum backing. And the tungsten anode that's actually mixed with rhenium, because tungsten and rhenium allows it to be a little bit more expandable as it heats up. At any rate, then you have the bearings that are in there, and you have the rotating rod that this whole thing is on. Side note, when the thing gets turned on, there's 2 things that happen. There's a double switch. I didn't mention this. When the switch gets pressed down, the first thing that happens is it starts rotating the anode. So it's already warmed up because we turned it on, but it starts rotating the anode now to reach that 3,600 to 10,000 RPM. Then, once it's reached that speed, you'll hear it because of these bearings. It makes a noise, and you can hear the thing spinning in there. Then the rest of the press down is actually the X-ray generation. It does its thing on this side. So the X-rays are generated once it hits the plate. These are now X-ray photons. I want you to note, not all the X-ray photons get directed where we need them to be as well. The ones that were going to be useful to us are going to come out of a window right here in the X-ray tube itself. But some of them end up bouncing off at angles. The ones that are going towards the anode that decide they don't want to come down, they usually get absorbed by the anode. But the ones that bounce away from the anode towards the cathode side, they'll pass right through this glass. So because of that, there's a housing that's made out of lead lined cast steel to try and capture those excess photons that didn't want to do what we told them to do. That way, the whole thing isn't as radioactive as it could be. There's an amount that we allow that escapes me at this second. But that housing collects most of those. Um, but the X-rays that we need get generated, come out the X-ray window, and that is how X-rays are generated. Thank you.